Hello, YouTube. Welcome back to episode 84 of the Stanford MLSys seminar series. My name is Dan. Today I'm joined by Michael as my co-host. Today we are honored to have Travis Addair as our guest. So Travis is co-founder and CTO of Predibase. Predibase is the AI platform for engineers. They're platforms for serving and fine-tuning LLMs. Today, Travis is going to tell us a little bit about the serving side of things. A bit more about Travis. So within the Linux Foundation, he's the lead maintainer for the Horvath distributed deep learning framework. He's a co-maintainer of the Ludwig automated deep learning framework. In the past, he's led Uber's deep learning training team as part of the Michelangelo machine learning platform. And today he's going to be talking to us about LoRAX, which is, I think, a new solution for serving hundreds of fine-tuned LLMs on one GPU. So with that, Travis, feel free to take it away.
All right, thanks, Dan. Okay. All right, so as Dan said, I'm Travis, CTO of Predibase, and today I'm going to be talking about a new LLM inference paradigm that we've put out called LoRA Exchange, which we cheekily abbreviate as LoRAX, that allows you to serve hundreds of fine-tuned LLMs for the cost of one. And so, what I'll be digging into primarily today is going over the case for why you want to be fine-tuning lots of small large language models instead of just using big general purpose LLMs behind an API, and what some of the challenges, particularly on the cost side, that you're likely to run into will be if you try to go down the fine-tuning route, and why we created LoRAX as a way to address those cost concerns. So to start off with, let's talk about why we're here, which is the rise of large language models that's really taken off in the past year or so, and in particular since the release of ChatGPT in November of last year. And when you look at this narrative, it's very easy to draw the conclusion that this is all being driven by bigger and bigger models that are have increasingly more impressive and emergent capabilities, right? And so maybe you might conclude that what I really need to solve any problem is just the largest language model that's out there and that I can possibly get my hands on, right? But one thing we like to say at Predibase is that bigger models aren't always better when it comes to AI. And one of the ways that we think about that is you say, well, general intelligence is great, like being able to do all these different tasks is great, but I don't need my point of sale system to recite French poetry. And by that we mean, if you're going to be putting a system in production to do one specific thing, and you want that to be as cheap, as low latency, as high throughput as possible, you don't want to be paying for all of these parameters in the model that are doing things that you don't care about, right? And you're paying for it one way or another, whether that's through the overall total cost of ownership or in the latency, et cetera. So kind of breaking this down a little bit more, the way that we like to think about is, these general purpose large language models that sit behind APIs like GPT-4, I think they've really changed the game for ML and AI and data science in a big way by giving you a really easy entry point to start getting something like a proof of concept or even something quick and dirty into production. Whereas before it would have cost you, months of research time to get anything, even close to production, right? But once you actually have it working and you have it, generating data, you'll quickly find that these systems tend to be more expensive and slow and overkill for the types of tasks that you typically do in a more enterprise setting. And there are other downsides as well, like giving up access to data and not being able to own the IP. But for the purposes of this talk, we'll mostly be focusing on that first point, which is the slowness, the expensiveness, and what we can do to mitigate that. So what you can do instead is think about taking your general purpose model as a starting point, and then from there kind of thinking about each of the specific tasks that you're trying to perform with that model, and building more specialized models on your proprietary data to solve each of those tasks. And it turns out that the kinds of models that you find in the open source today, like Mistral 7 billion, Llama 2, even like more classic models like BERT that kind of predate the LLM revolution, tend to be good enough, if not even better in some cases, than these general purpose models once you fine tune them on your data. and since they have a much smaller form factor, tend to be a lot faster and potentially a lot cheaper. And so as one simple example of this, we did some benchmarking internally for one of the use cases that we see a lot of our customers asking about, which is extracting structured semantic information from raw unstructured text. And you can start with a model like GPT-4 down here on the left, or even Llama 2 70 billion, like a very large open source model. And you can see that, the large open source model does okay, 33% accuracy on this task. GPT-4 does much better, 66% accuracy. But fine-tuning a model that's, orders of magnitude smaller, like Llama 2 7 billion, gets you suddenly a huge bump to 93% accuracy. And then if you really care about that extra delta, you can even go further with Llama 2 70 billion and get slightly better. But I think the real selling point here is, you go from general purpose large language model getting you decent results to specialized, much smaller model getting you really strong results. And that's all made possible through fine tuning. So in practice, what we believe is going to happen is people find that they'll have these individual tasks that they need generative AI for in some capacity. And what you're going to want to do is serve multiple of these fine-tuned models in parallel. And some potential ways that this can manifest is, maybe you're an AI platform supporting multiple customers, and so you need to support many fine-tuned LLMs for that reason. So that's the kind of use case that describes us at Predibase and sort of why we built out this technology in the first place. But even customers who don't want to do multi-tenant serving, we have some customers who want to do dedicated deployments in their VPC, et cetera. We still believe that there are many applications for serving multiple LLMs in parallel. A really good one that comes to mind from my time at Uber was segmented models, where you have a single task like predicting something or doing some sort of classification, et cetera. But you might have a different user or product or region, et cetera, that you're trying to apply it to. And so you might end up building a model per user, per task, per product, et cetera. And we saw lots of examples of this at Uber where we would commonly, build models per region, for example, but there are lots of people we've talked to that end up building models per customer because their customers have very bespoke data requirements, et cetera. Another good one is agents and workflows. I think this is kind of a newer type of thing that's emerged thanks to large language models and kind of chain of thought prompting, et cetera. But oftentimes in these chains, you'll want to perform certain tasks along the way. Like, for example, you might have a customer support bot that you want to implement, and along the way, you need to determine what type of issue it is and route it to the correct system to handle it, and then process the payment and process other remediations, and then generate a response back to the user. And so every one of these steps along the way could, in theory, be its own fine-tuned model that's specific to that one task. But as soon as you start, kind of imagining this new world of having all these fine-tuned large language models in production, you quickly start to run against this wall of okay, well, wait a minute, how much is this all going to cost once I go to production? And so, different GPUs cost different amounts in different clouds, et cetera. One kind of anchor that we like to point to for, let's say, Llama 7 billion. Llama 7 billion is about 14 gigabytes in memory without thinking about the activations, et cetera. And so what we typically see is that the A10G, which is the G5 instance type in AWS, has 24 gigabytes of VRAM and tends to be about the sweet spot for loading something like a Llama 2 7 billion model for inference. And if you're running that on, kind of the low end of the instance types, it's about $1.21 an hour to run dedicated without any, without any pre-committed spend or anything like that in AWS, right? And so for the purposes of a lot of the cost computations we're going to anchor on that $1.21 per hour number that goes along with the G5 instance. And so, very quickly you'll realize that this balloons into the thousands and tens of thousands of dollars per month very quickly, right? So here's the cost running one fine-tuned Llama 7 billion model 24/7 in AWS without any kind of special credits. You're going to spend about $871 per month. And then as soon as you get up to 16 of these models, you're already crossed the $10,000 per month threshold, and then it just continues to go up from there, right? So if you have just on the order of 10 tasks or so, you're already getting up to many thousands of dollars per month. So what can we do to mitigate some of these cost concerns? And before I get into the details of LoRAX and like how that fits in the equation, I first want to talk about the idea of parameter efficient fine tuning, just as a quick primer for folks. So in traditional fine tuning, which was like, how most people were doing it, 8 months ago or something, right? You have a data set, and then you have a pre-trained LLM, and then you're going to basically, as part of your forward backward pass, your stochastic gradient descent, you're going to update all the parameters of the model in each step, and the result is going to be very large amounts of memory that you need to track in your optimizer, which is about 2x the number of trainable parameters, very large gradients, which is about 1x the number of trainable parameters, right? And very large checkpoints, which are going to be on the order of like 14 gigabytes, for a Llama 7 billion model. So can we do better than that? Well, it turns out that because LLMs are so big and these training processes are so memory hungry, parameter efficient fine tuning has really taken off as the preferred alternative for doing fine tuning of large language models. And the basic premise behind this is that instead of fine tuning all the weights of the model, what we're going to do is add a few additional parameters, which are represented in blue here, alongside the parameters of the original model. And then we're only going to train those new parameters, right? And so usually those parameters are somewhere between like less than 1% to at most about 10% of the total memory of the original parameters. And one of the most popular techniques for doing this parameter efficient fine tuning is what we call low rank adaptation, or LoRA. And the idea behind LoRA is actually very simple, is you have the pre-trained weights here on the left, which, in this example is 1024 by 1024. And then you introduce these two new matrices, essentially. One is called A, one is called B. And they're both low rank, meaning that there's this R term here that you can set, which determines what the rank of these matrices are. It's usually like 8, sometimes 16 or 32. But the nice thing about having this kind of representation like this decomposition, is that it means that storing these parameters is very, very cheap, because these are both very small matrices, right? And so they end up being only about, in this case, 1.5% of the weights of the original W matrix, right? And these are the only parameters that you're training in this case, are all of these sort of, new parameters that you introduce alongside the original ones. And so, kind of net at the end of the day, you're only training 0.5% to 10% of the model parameters. And then in practice, what happens, in terms of how this affects the model is, you run the forward pass on both of these things during inference time, and then you just sum them together. It's super simple. So nothing particularly fancy that you need to do on inference to make it work. So now that we've kind of talked about like, what is LoRA, how does it work as a way of fine tuning the model cheaply, let's talk a little bit about LLMs as deployments. So a typical LLM deployment will consist of a few components. You have a user submitting requests. Those requests will typically go into a queue of some sort. And then the model itself is going to be loaded into memory inside of your container or instance. So in this case, we typically run on Kubernetes, so it's going to be living inside of a pod. And then, you're going to have your model weights, which are going to be here represented in this kind of orangish color. And then you're going to have your adapter weights, which are going to be these smaller set of the parameters that live alongside some of the layers in the model. And then if you want to deploy multiple of these, you still have this problem of, well, even though I've fine-tuned only a small portion of the weights, I still need to spin up another pod, which is another GPU for this model. And then, I have user 3 coming in who now is submitting a new request, I need to kind of serverlessly spin up yet another pod for this user, and on and on and on until I've, spent tens, hundreds of GPUs, right? So there must be a better way to do this. And this, of course, comes back to the insight that, well, if you look at these different deployments, right, again, the vast majority of these weights are exactly the same. It's only these really small, adapter parameters that are different. And so you can imagine like, well, I would ideally want to just fit all these parameters into memory within that same deployment, right? So that's the key idea behind LoRA Exchange or LoRAX, which is our LM inference system for fine-tuned LLMs. And at a high level, LoRAX consists of three key components. The first that we call dynamic adapter loading. So the ability to load these adapter weights just in time when requests come in. Multi-tier weight cache that allows us to do offloading and preloading of weights in the background so that we can keep up high throughput, but also be able to support a very large number of adapters that might be in use at a time. And then finally, continuous multi-adapter batching, which is an extension to the popular LLM inference technique called continuous batching that basically allows us to take requests from multiple adapters, fit them into the same batch, and then send them all through the LLM and inference time together without having to do any kind of like, let's do this adapter, wait, now do this next adapter. So I'm going to talk about each of these techniques in turn. The first, dynamic adapter loading, I think is pretty simple. So you can imagine we have three different users here submitting requests. And then instead of just loading one of their adapter weights and allowing those requests to proceed, we go ahead and load multiple of these weights. And so in the case of user 3 here, instead of in the previous example where a new request results in a new deployment, here a new request just results in new model weights, new adapter weights rather, being loaded alongside the existing weights. Now, you might reasonably say, well, what happens if, you take this to an extreme of like saying hundreds of models or thousands of models, like what do you do in that case, right? And that's where the multi-tier weight cache comes into play. So effectively, we have caching at three different levels. The first level is the GPU, which is where all of the adapters that are currently actively accepting requests reside. And so we do that so as new requests come in, we can very efficiently send those requests into batches, run them through inference on GPU, and then send the results back to the user, right? But beyond that, we also have a CPU cache that we can fall back on when we start to reach the limits of what can fit on GPU. And so we tend to prioritize putting adapters that are in what we call the pending queue into CPU memory. And so in this case, these are adapters that are waiting their turn, essentially, to become active. And so they're staged in CPU memory or host memory so that when the scheduler, which I'll talk about in a bit, decides that it's time to swap out or exchange one of these adapters with one of the pending adapters, they can very quickly be hot loaded onto GPU in the background without having to, do like a costly disk read or something like that, right? So all of this, again, is something we can do asynchronously in the background. So we can preload these weights onto the GPU without having to block requests. And we can offload these weights back to CPU without having to block requests either, once something goes from active to pending. Finally, we have what's called the idle tier. And these are adapters that are not currently, don't have any incoming requests in flight. So maybe, there was a burst of requests for some adapter, then all the requests died off. What do we do in that case? Well, we still like to keep the weights around in case new requests come in the future, but we don't prioritize them as highly as the requests that are pending or active, of course. And so the tendency there is to just let the weights reside on ephemeral disk storage and then read those in as necessary, and then potentially, write them back out if we need to. Usually the write is a no-op because they're already saved on disk, but if we have to, we can write them out again as well. And that's just to, ensure that all these weights are freely available if needed without having to go back to persistent storage like cloud storage to retrieve them. And the third innovation that I want to talk about is what we call continuous multi-adapter batching. And so the basic idea behind continuous batching is that, you can basically, as you're going through the decoding step in LLM text generation, as requests complete, you can take a request that is completed and remove it from the batch and insert a new request into the batch so that it can kind of continue decoding along with the others, even though they're at different steps in their kind of decoding journey, right? And that's one of the key ideas that's been introduced by frameworks like Hugging Face's text generation inference and VLM that have, made this that basically led to very high throughput in these serving systems. So obviously, we wanted to make sure when we implemented LoRAX that the benefits of continuous batching would still be available to users. We didn't want to end up in a situation where you could only do continuous batching for, say, one adapter at a time, in which case you have kind of an issue when you want to swap out adapters, right? Because if you can only do one at a time, if you want to go and swap to an adapter, you have to wait until all of its requests finish until you can swap to the next adapter. And what that means in practice is that you're going to have very low GPU utilization during kind of the warm up and then cool down phases of the decoding process, because you're going to have like just a few requests that are like taking a long time to finish because they're generating lots of tokens. And during that time, you're not allowed to admit any new requests, and the whole thing is going to be really slow. So obviously this was important for us. And so the way that we managed to achieve this is actually pretty simple in practice. So you have, we kind of just blow out one of the layers here for illustrative purposes, but you have the layer weights from the original model here in kind of light orange, and then you have the adapter weights here. And then in front of each of the adapter weights, you have a mask. And the purpose of the mask is to basically zero out the contribution from adapters that don't apply to a particular row in the batch. And then finally, you just sum up the results of applying all these adapters to the original output from the base model weights, and that becomes the final output that gets sent to the next layer. And so what you have on the right is just some basic pseudocode that shows you how this works in practice. You run the input through the base layer. For every adapter that's in the active layers, you check and see if there's that adapter happens to be in the batch. If not, you just continue. But if so, then you define the mask to be the adapter IDs, which is like you can think of this as just a vector, right? The adapter IDs are a vector where like every item corresponds to the adapter ID for a particular row in the batch. And then you create the mask to be like, does the adapter ID at this particular index equal the adapter ID for the current adapter? And then you get a vector of ones and zeros. And then you just multiply out that the output of the adapter with the mask, and that gives you your final output. So those are the three main ideas in practice. And now what I want to do is talk a little bit about the actual batching algorithm that kind of underpins this whole process and kind of puts it all together. So the batching algorithm of LoRAX looks like this. We have N adapters that are active on the GPU at any given time. And then we batch requests from active adapters together by timestamp, meaning that we always take whatever happens to be the globally oldest request across all the active adapters and add that to the batch when we have an opportunity to do so. And then we apply LoRA weights during the forward pass and mask out the rows post hoc. So after applying the adapter, that was what I showed you in the previous slide. And then after a parameter that we call the cycle time, T, has elapsed, we're going to exchange the oldest active adapter in the active set with the adapter that's been waiting in the pending set for the longest. And this T parameter is something you can configure. So if you set a higher T, that means you're waiting longer to transition to sort of exchange out adapters. And that gives you higher throughput at the cost of latency. And so conversely, if you want to have a lower T, which means that you're swapping out adapters more frequently, you're going to decrease the overall latency, or average latency rather, but at the cost of some throughput benefits, because you do get some nice throughput benefits by letting adapters just kind of run wild and feed requests through the system at once, right? And then finally, we'll offload any what we call idle active adapters if the adapter, if there are adapters that are waiting in the pending queue. So basically that means that there's an adapter that's in the active set, it has no requests. There's another adapter waiting and pending to take its place. So we're going to move that active adapter to idle, move in the adapter from pending, and we'll continue this backfill process until there are either no pending adapters left or no idle adapters left. So I realized that that was a lot of words, and sometimes it's better to kind of visualize what's happening. So here's a quick kind of visual illustration of this process for a very simple example with 3 adapters. So in this example, we have A and B in blue and red that are listed as active, and C is currently pending. And then our scheduler currently has the cycle timer at 0, which means we've just kind of initialized the whole thing. And these requests here are numbered based on their timestamp. So 1 is the first request, 2 is the second, etc. So in the first step, what we're going to do is fill our batch based on what are the oldest adapters that are, the oldest requests rather, that are waiting in the queue. So 1, 2, and 3 get filled in. And this is again in kind of first in, first out ordering. So 1 and then 2 and then 3. In the next step, B is now empty because we've moved all of its requests into the batch. But we can't at this point move it out of the active set because it still has requests that are being decoded in the batch, right? So we need to wait for its final request to complete before we can kind of swap it out. So in the next step, all of B's requests have finished. So we're going to go ahead and move it to idle, which happens here. And that means that C is going to step in and take its place and become active. Now in the next step, we go ahead and fill in requests from A and C, again, based on kind of the total ordering of the timestamps. And at this point, new requests are coming in for B. So it's no longer idle, it's now pending. But because A and C are still active and the timer hasn't elapsed, those requests just need to kind of wait their turn. Now in the next step, we've hit our cycle timer, which in this example is 3 seconds. And so now what that means is we're going to stop accepting any new requests from A, again, while we wait for any of its active requests to finish. So any of the requests that are currently in the batch to finish up. And finally, at this point, all of A's requests complete. And so as a result, we're going to go ahead and move it to pending. And then that means that B is going to go ahead and take its place once again. And this process will continue and B will start filling in its requests and on and on and on, right? So that's the process in a nutshell. And then, what about how this translates into actual numbers? So here's some empirical results that we have from our tests that show what the throughput is as we layer on more and more adapters. And in this particular test, what we were doing is kind of trying to overload the system as much as we could with requests, right? To kind of see, what it looks like at very high utilization across all adapter types. And one thing I'll point out is that we also define what we call this break-even threshold here, which I'll talk about a little bit more in the subsequent slides. But the basic premise of the break-even threshold is that we want to define what's the point at which the throughput is so bad that we'd rather just not do this LoRAX thing at all and just go back to like using dedicated deployments. And luckily, what we've observed is that the degradation in throughput, like there is some degradation in throughput as you add more and more adapters, right? I think that's not too surprising. Here we're doubling the adapters each time. But the good news is that that degradation is somewhere between 20 to 30% as you double the adapters, past kind of the 2 to 4 regime, which is really not too bad in practice. And so you can get all the way to 128 adapters over here and still get pretty decent throughput. Obviously not nearly as good as if you have only one adapter, but that just gives you a sense for, even at very extreme cases, which I think 128 is probably more extreme than you would want to go in most cases, unless you have very little utilization, you're still getting like pretty decent results. Latency is kind of similar. You can see that, latency per token in this case sits below 1 second, even as you layer up to 128 adapters, at most it gets to 0.56 seconds per token, which again is not great. But again, this is under, very, very heavy load where every single adapter, all 128, are getting a constant stream of requests. Not too bad, I would say, in that case. So one last thing I want to do is dive into kind of the actual dollars and cents ROI of this. And I think this is a little bit difficult because there is no really good apples to apples comparison between this kind of LoRAX-based adapter serving and just normal dedicated deployments. But the way that I've tried to think about it is with this thought experiment. And you guys can tell me if you think that this is not a very good way of thinking about it, but this is the best I've come up with so far, is if you consider an infinite stream of requests coming in uniformly distributed across all the adapters, you can imagine that, like in the extreme case, if throughput was incredibly slow with LoRAX, at some point it would be more cost effective just to run on dedicated compute, right? This is like that break-even threshold that I mentioned before. And so as an example, if you 2x the number of adapters that you were serving in LoRAX, and it got more than 50% slower than it was before, you could say, well, I might as well just go ahead and 2x the number of GPUs instead, because, for the same amount of time, it's going to complete, or for the same, for 2x the GPUs, it's going to complete, 2x faster, whereas I'm getting, more than a 2x slowdown with LoRAX. So in terms of like how long I'm having to, let's say, rent the GPU for this amount of time, it's just more practical to not use LoRAX, right? So that's kind of why we set that 50% degradation for every 2x adapters as what we call the break-even point there. And obviously it depends on your own requirements around latency and throughput, but that's like one very simplistic way of thinking about it. And so for this analysis, what we did is we said, let's let the cost per GPU be $1.21 per hour, which is the G5 2x large cost. And then the baseline that we're going to use is the throughput under continuous load for one GPU and one adapter over some fixed request window. And then let's define our baseline cost to be 1 over the tokens per second, so 1 over the throughput, times the cost per second of renting the GPU, times the number of tokens that we're generating in that window. And then let the cost of the dedicated deployments for N GPUs be the cost of the baseline times N. So that's kind of the equivalent cost of doing a dedicated deployment. And then let's let the cost for LoRAX deployments be, for N adapters, be the observed throughput using this same baseline formula, where the throughput here is the throughput at N adapters, right? And what that works out to in practice is something like this, where you see, cost per million tokens in dollars. If you were to just rent, 1, 2, 4, 8 GPUs, et cetera, with dedicated deployments, you see that very quickly balloons to something very expensive. But with LoRAX, even as you get up to 128 GPUs, while the cost does increase because throughput is decreasing, it's still way, way, way below what you would be paying for the equivalent of renting those dedicated GPUs. Last thing I want to talk about before kind of opening up to questions is kind of the higher level perspective of how this fits into an ML platform. So at Predibase, we have infrastructure that runs on Kubernetes. So we're not just talking about one LLM deployment, we're talking about a set of replicas of the deployment that need to be load balanced across. And one thing that you can do as an additional layer on top of LoRAX is have a sort of consistent hashing strategy within your load balancer that makes sure that adapters for similar adapters go to similar deployments, which is important because if you want to make full advantage of continuous batching and not kind of reach that 128 adapter scenario that we were talking about before, you want to try to keep your adapters together on similar deployments. And so, this is an additional optimization you can do on top to constrain the number of adapters that each replica is having to deal with, so that you're not, just uniformly distributing all the adapters across all the replicas and just overwhelming the system, right? And what's next? For LoRAX, well, we're open sourcing it soon, hopefully in the next week or two at most. We're also going to be working on adding a support for more adapters. So for example, instead of just LoRa, maybe you want to have a classification head on top so you can do sequence classification. There are other cool innovations out there using adapters like Medusa, which is a way of like speeding up decoding with speculative decoding. TART, which was some work from folks at Stanford that allows you to kind of get the benefits of fine tuning without really having to do fine tuning. More generalities, so making it easier to add support for any layer in the model, any model type. Currently, we support Llama and Mistral, and then embedding models. So for retrieval augmented generation, this is a really popular one right now. You can fine tune a multi-layer perceptron on top of your base embedding model, and that's a very cheap and efficient way to improve the results on retrieval for your particular corpus, right? So that's something we're looking to add to LoRAX as well. All right, and so in summary, don't do this, do this, use LoRAX, and check out Predabase and Ludwig. You can try LoRAX for free at Predabase, pbase.ai/get started. All right, and I'll go ahead and hand it back to you, Dan.
Well, thank you so much, Travis. And yeah, thanks for stopping your screen share there. Yeah, this was a really, really great talk. Really, really interesting. I think we have quite a few questions in the YouTube chat and also in the Discord. I'm just seeing now. So if you're watching online, feel free to ask questions in the YouTube, and we'll get them to Travis. I'll just go ahead and start out to at the beginning. So I love that you mentioned TART at the end. It's I think a really interesting piece of work from some of our lab mates. For those who are unfamiliar, one of the questions in that work was how can we make a off-the-shelf LLM match the performance of a fine-tuned one without kind of going through all that fine-tuning. I wonder if you could offer some color on that. If you think, how will something like that, if it works out, change the I guess kind of the landscape of the solutions that you offer and the bottlenecks? I guess as one point of view, I get OpenAI has recently started offering like customized GPT-3, customized chat GPT, which my guess is it's just some form of prompting. But do you think techniques like that could one day catch up to fine tuning? How does that kind of change your calculus of how you're going to serve these LLMs?
Yeah, absolutely. And yeah, we're definitely big fans of TART. We're working on to add it to Ludwig at the moment, which is our kind of fine tuning open source project, which then feeds into what we serve in Predabase. And the way that we think about it is the biggest challenge that we see from users when they come to us initially is, hey, I've got something working in OpenAI or whatever, but I don't have a data set of like 1,000, 10,000 examples ready to go for fine tuning. How do I kind of start that process, right? Like, how do I overcome this cold start problem? And I think that in context learning has been a very, effective way of kind of saying, all right, well, you can get started with like 10 examples or so, but that doesn't really solve the problem, right? Because you're still prompting this very general purpose LLM that's super expensive. And, it's not going to get you to the benefits of fine-tuned LLMs and LoRAX, right? And so the nice thing about TART from our perspective is that, here's a way that you can take a base model like Mistral 7 billion and do some very lightweight statistical analysis of a handful of examples, like 10 to 100 or something like that. And then that gets you a very small adapter that can specialize it to some particular types of tasks that you might want to perform on that data, right? Which we think can be a very compelling way of bridging that gap of like, okay, I can generate, some examples like 10 to 100, but I don't have a full data set ready to go, right? And we think that, users will naturally collect larger and larger data sets over time as they run more inference and they get more exemplars of like what a good output looks like. But if you want to get started, I think that TART is a really good way to do that, and certainly might even be good enough for the task just in general if it's not one that requires tons and tons of data to do well at.
Cool. I think another, interesting question, and that we also saw coming from the YouTube chat a little bit. So there's one question: how do you make up for kind of the relatively poor quality of smaller models? And I guess as a follow-up to that is, what are you seeing kind of in deployments, or like what is the difference between a Llama 70B, a GPT-4 versus kind of a smaller model? Is it kind of the facts that they know, or reasoning patterns, or something like that? Are you seeing any patterns there?
Yeah, so I definitely like to think about it on a task by task basis, right? And it very much depends on what is the complexity of the task that you're trying to get them all to perform. And so a really good example of this is we see a lot of people come in who want to use large language models like Llama 70 billion to do multi-class classification, where there's like 3 or 5 different classes that you're trying to predict. And I would say 99% of the time, you're probably going to be better off using Deberta, which is like 350 million parameters and is from like a few years ago, to do that task, than you are going to be, using like a very large language model to do it. So it's very task specific. Now, I think one area where what we truly call LLMs like starts to be a lot more beneficial is in these sorts of generative AI applications, right? Where it's like text generation for some application. And there, again, I would break it down by task and say that if you're trying to do like an extraction task, like unstructured to structured data, even some tasks that are relatively constrained, like SQL code generation or Java code generation, et cetera, the smaller models actually do quite well at that, I would say, in practice. Even retrieval augmented generation, where the main goal of the LLM is to synthesize the context that's been given, right? You see, for example, Zephyr 7 billion from Hugging Face outperforms GPT-4 in a variety of tasks in that regime, right? And so really where I would say the large language models tend to shine is on the very general tasks, like being a chatbot, like being a very general purpose chatbot, which I think they will continue to probably be the best at for some time. But those are cases where, you're not generally going to be wanting to do fine tuning for like a specific task anyway, until you realize like, hey, there's a specific prompt pattern that I'm doing as part of my chat, over and over again. Maybe I should go and build a task specific model just for
I
that.
see. Okay. So do you kind of so coming from academia, one of the things that I had assumed was that fine-tuning, a chatbot was something that people actually wanted to do so that you could, I don't know, talk to your corpus or something like that. Is that something that you see people do, or less so?
I think that there is still an application for fine tuning, a chatbot, but I would say that for talking to your data, most of the benefit comes from the retrieval augmented generation process, which means that you're getting most of the benefit from how good is your retrieval step, right? Which, if you're doing vector search, means how good is your embedding model, right? But it doesn't have to be. Maybe, your retrieval step is, the user has this intent. I have a SQL database somewhere that has some data. And then how do I translate their intent into a SQL query to then fetch the context, right? So there are different ways that you can also think about the retrieval step. But then on the synthesis step, where you're basically saying, okay, here's the context, now answer the user's question. That part, I would say the models tend to be pretty good at natively. And Zephyr, I think, is one example of one that's particularly good at that synthesis step. But we found that, using even off-the-shelf Llama 13 billion, 70 billion tend to be pretty good at it. I will say that Llama 7 billion, Llama 2 7 billion we found was not particularly good at that synthesis step. So there is some benefit to that. But that would be one case where you would want to fine tune just to be better at that last mile synthesis step. But where I'm saying that the kind of general purpose like GPT-4s of the world tend to do really well is really less so on specifically retrieval augmented generation and more on kind of those unbounded, unconstrained multi-turn conversations where it's not very clear like what are the parameters with which this task is to be bounded by, right?
Cool. Right. Gotcha. Yeah, that's yeah, I think that's some really nice insight, and love to hear it kind of from our side where we're not touching these things all the time. We're getting a few questions about, I guess, kind of more technical things, so we can dive a little deeper and, things that I think people are just curious about hearing the conversation. So one of them was, have you explored combining LoRAs together? Like if you train two LoRAs in a mixture of experts fashion or combine them and merge them in some way, have you looked at that at all?
Yeah, absolutely. So this is actually one that I haven't done myself yet, but I have it as like I actually should have put it on the like future work side. So um, I think the person who asked this may be familiar, but maybe not everyone is. But there's this concept in diffusion models called like LoRa sliders, right? Where you can basically train a set of LoRa parameters to kind of forget some part of the model. So it can be like, this model will never generate red hats or something like that, right? And then you can kind of use that to as kind of a sort of filtering mechanism to remove stuff from the image that you generate, right? So I haven't seen a lot of actual literature on this, but like the hypothesis that we have is like you could do this very similarly for text generation as well, where you could say like, as an example, like let's fine tune a llama model that generates Shakespeare, and then a llama model that generates Faulkner, and one that generates like Tolkien or something, right? And then you could imagine instead of masking as we do now with like zeros and ones, you could kind of have a bit of a weighting mechanism, right? Where it's like 70% Faulkner, 30% Shakespeare, and kind of slide those things around and kind of blend the results together. And if surprising thing was that this actually worked in diffusion models, right? And so it might actually work pretty reasonably in large language models as well, where you could find a cool way to kind of be like, all right, I want to generate text that's kind of like this, but and maybe a little bit more like this and not like this, right? And kind of mix and match on the fly in that way.
Gotcha. Yeah, it's really interesting. If you guys run some of those experiments, would love to see. Would love to hear about it. Um, on another side, on kind of more of the systemsy serving side, I really love that kind of multi-tier weight caching thing that you presented. It's so obvious that there's, GPU memory and DRAM and then disk. Have you thought at all about, or does your system, I guess, extend beyond that? So obviously, there's also this other giant, layer of the memory hierarchy, which is just network. So does your system kind of automatically look at when it's time to pull down new sets of LoRa weights from the network? Do you start hot caching that, or when would it make sense to start thinking about that?
Yeah, that's a good point. So we definitely do store our weights persistently in S3, for example, like in AWS. And so we have done a lot of work to optimize that download process as much as possible. But yeah, it definitely is something to have in the back of your head that, if you get a bunch of requests at once, you're going to be, saturating your network interface, right?
Right.
So how can you optimize that in some way? I will say that we haven't done a lot of work to optimize that. Right now, we do like just in time, like, okay, go download the weights, right?
Right.
Particularly for adapters, I will say that it tends to be pretty snappy in practice, though, because the adapters are so small. Right now, we see latency on the order of about 200 milliseconds to download the
Oh, okay.
adapters. So, yeah, at the moment, it hasn't become a bottleneck, but if this really takes off, I could definitely see us revisiting those assumptions.
Right. Okay, so I'm just getting a couple from YouTube chat right now. So I'm going to look this way because that's where my YouTube chat is. I tried to copy it onto the screen, but it failed. So one question is, how does LoRAX scale when the load goes up? And as you're starting to deal with this dynamic adaptation, will you have to worry about saturating the infra because of kind of added complexity to deployment and dynamics? And then there's another question from the same person. So the uniform model and deployment can be expensive at runtime, but it should just scale like kind of horizontally in the most cases, especially at very large scale. So how do you kind of think about those factors?
Yeah, absolutely. So this kind of comes back, and I guess this will be one example where I'll go ahead and share my screen here. But uh, yeah, so it kind of comes back to something I showed earlier, which was the throughput slide. So throughput versus the number of adapters. And so this is kind of the way that we think about, what is that that limit or that bound that you have effectively on, as you increase the number of adapters, what does that do to performance degradation, right? And so it definitely does degrade, right? There's no doubt that there's some cost to like packing tons and tons of adapters at once. I will say that in this example, though, like we were very careful to try to examine a worst case scenario, which is like, you have 128 adapters and you have a continuous stream of requests coming for all of them at once, right? And so one thing that, I think is very important is that in practice, a lot of these adapters are going to have very bursty or sparse request patterns. And so you're very unlikely to see a pattern quite like this unless you're, like a hyperscaler type user, right? And so the way that we think about it is we will try to kind of aggressively pack in different models if we're seeing that QPS is relatively low. But if we start to see, high utilization, high QPS, that is a good opportunity to scale up like a replica that's like only for that adapter, or that's, limited in some way in the number of adapters that it'll support because of that, high amount of load. So that's the way we think about it. Some of those optimizations are still, I think, a bit forward-looking because we're still pretty new in this process, but that's kind of the way that we think about it. And definitely, I think it's different if you're a company like Predibase that's like, okay, we're multi-tenant, supporting all these different users who want to run these fine-tuned models in parallel, versus you're doing this like in a dedicated deployment where you have 10 to 100 adapters that you want to use in production that have certain SLAs. And in those cases, what I would do is actually look at these numbers and say, am I comfortable with that amount of throughput at 16 or 32 adapters? Am I comfortable with this amount of latency at these adapter levels? And if not, then that's where you kind of back off and say like, okay, what is the acceptable worst case scenario latency that I'm willing to accept, right?
Gotcha. Yeah, that's very interesting, and would love to, maybe you guys don't want to release it, but would love to kind of see what those traffic patterns are, and or maybe not your actual traffic patterns, but like in general, like here's this case, here's another case. Would love to. I'm sure people would love to just sink their teeth into that, and then look at the various things that you can do with kind of different traffic patterns there.
Yeah, me as well. I think I'm looking forward to doing a deeper dive into it at some point.
Cool. So we are getting close to the end of the hour. So I wanted to. There's kind of one higher level question just from the chat that I want to ask, and then I'll just let you talk a little bit about if there's anything kind of like exciting coming up that we should be watching out from Predibase. But that kind of higher level question from the YouTube chat was, what's your view on kind of LLM commercialization as a SaaS model? How are you kind of like seeing it work out, or generally, speak to that and what your thoughts are on it?
Yeah, so I think in terms of LLM commercialization, I think about it in kind of two buckets. Like one is the consumer side and the other is the enterprise side. And so on the consumer side, I think that the kind of API oriented LLM services like OpenAI, whatever Elon Musk is doing with XAI, presumably, Anthropic, et cetera, Bedrock. I think that those are, well, maybe not better, but I think that those like kind of user facing ones are, very well suited to consumer applications where, there's like a high degree of generality that's needed. And again, there's like not a very bounded task definition, right, that needs to be applied to the usage patterns. So I think that those will be here to stay for that reason. But I think on the enterprise side, which are companies building LLMs for their own specific purposes, I think that it's going to break out in a few different ways. Like one, you have companies like, let's say, Midjourney that, want to build their own specialized models to build their own user consumer service on top of it, right? And they're going to have their own needs. They're going to need their own stack and developer suite for that. But then you also have companies that have what you would call more broadly just like generative AI applications, right? Like I need to summarize text. I need to build a customer support agent system, right? I need to extract structured information from my unstructured data. I think in those applications, things like LoRAX, things like fine-tuning platforms are going to be very valuable to derive value in those cases. And so that's where, in particular with us on Predabase, we're trying to focus our attention, because we do believe that like our bet, if you will, like on the future of the market, is that for that segment of customers that want to use generative AI, that they're going to want to build systems that work particularly well on their data, right? They're going to want to own those models as their own IP, as opposed to kind of renting it through an API. And they're going to want a solution that's faster, cheaper, more scalable than what you get with the SLAs provided by, the LLMs as APIs solutions out there, right? So that's effectively our bet on the future for LLMs.
Cool. I'm excited to see how that plays out. And just a last question as we kind of we close off the hour. You kind of touched on it a little bit with that last answer. But what's kind of next coming out of Predabase? What are the things that you're excited to work on and be releasing soon?
Yeah, so there are a few things coming up that I'm really excited about. Obviously, expanding the scope of what we're doing with fine tuning and LoRAX and like deeper integration between those two things. So, anything you fine tune in Ludwig on the open source side or in Predabase on the commercial side, we want to be able to be very efficiently served using LoRAX, so that you can fine tune and start querying immediately, in the order of like milliseconds, and have something in production very fast, right? I also think some of these innovations on reducing the data barrier to getting value from fine tuning, like things like TART and some other things that we're working on, I think those are going to be very pivotal to, allowing people to bridge that gap between the APIs and, something that they own themselves. So those are a few things I'm particularly excited about. A little bit more tactical things that I'm excited about. We're releasing like a very self-service version of the product very soon. Like right now we have a free trial that anyone can go and try out for 14 days. We also, talking with our sales team, you can kind of like set up a consumption-based pricing model for running it in SaaS or running it in your VPC. But, in the next few weeks, we're going to have a completely self-service, like you don't have to talk to anyone at Predabase, you just swipe a credit card and go kind of version of the product. So we're really excited to be releasing that. And then we also have built out our own A100 cluster with dedicated compute. And I think unlike a lot of other companies that kind of, just route all traffic there, we've actually built a pretty interesting, what we call a GPU arbitrage system on top, where we can decide like, all right, should we send it to our own A100 cluster for computation based on the level of demand that we're seeing, or should we send it to a more elastic cloud like AWS, depending on what the expected wait time of the job is and the expected cost of the job is, right? So those are a few different things that we've been working on that I'm pretty excited are going to be releasing soon.
Cool. Yeah, that sounds very exciting. And looking forward to seeing all that come out. So that brings us to the end of the hour. So I just wanted to thank you again for coming on, and thanks everyone for tuning in and asking some great questions. Michael has been here behind the scenes, kind of running some of that Q&A. So he didn't I didn't put him on camera this time, but you should give him your kudos in the chat. So you can go to mlsys.stanford.edu to check out our calendar and our schedule. We have a mailing list that you can subscribe to that we email like maybe once a week. Of course, if you're on YouTube, subscribe to the YouTube channel, hit that bell icon to get notified when we go live. Next week, we've got William Fettis from OpenAI. So we're very excited to have him on and hear what he has to tell us. And so with that, we'll wave goodbye to the audience, wave goodbye to YouTube. And thanks so much for tuning in today. Bye, YouTube.
Thanks, everyone.
Okay. I just saw